Recording unpaused. Okay, thanks, Lupe.
That was Alyssa, by the way, on the chat.
Oh, that was in the chat? Oh. I wish I could like say a magic word and then the chat window would appear. But it ain't. Pardon me while I try to configure. There's the chat behind that. All right. Yeah, thanks, Alyssa, for reminding about the recording. And yes, I need to make a note about adding links to past recordings to the Canvas site too. All right, derivatives. So what I'm going to start doing today is I'm going to start developing the ideas that will help us understand the concept of derivatives. And the core idea, the gut level idea behind a derivative is that we take a derivative is an idea associated with a function. And this is the kind of phrase that we use when we talk about derivatives of a function. A derivative is an instantaneous rate of change of the function at a point. Okay, so I'm going to try to build up and give you all the vocabulary and the conceptual framework for understanding what this means. Okay, so we've just come out of a conversation about limits. So we're going to use limits to describe derivatives, and I'll explain how that works in a little bit. And we've come out of continuity, a conversation about continuity at a point and continuity on an interval. So the idea of differentiability, or when you can find a derivative of a function, it builds on top of the idea of continuity, and you'll see how that works in a little bit. But let me just remind you of something, and this is going to be a little repetitive from last time, but I really like it. I want to remind you what limits tell us about a function. So if you have some function, and you know the limit of that, the values of that function as x approaches c, if the limit equals the value of the function at that point, what you know is this means that f of x is continuous. At x equals c, okay? So very important statement about a function. It means the function is continuous at a point. So geometrically, what does that mean? Well, it can mean one of three things. So I'm going to draw three sets of coordinate axes here. It means that the function looks one of the following three ways. So all these graphs have the fact in common that the graph of the function is coming into the left, or coming into the point c comma f of c from the left, and then going out from the right. So the graph is passing through the point c comma f of c in each of these three cases, but it's doing it in a different way each time. And the limit does not distinguish between these. So this limit statement does not distinguish. So just from a computation of a limit, you can't tell what your graph, which one of these three ways your graph looks at the point C. The derivative is going to help us distinguish between these. Right? So the derivative is going to be another computation that helps us understand what a function is doing at a point. Is it like this and kind of coming downward? Is it like this and going upward? Or is it like this and kind of staying level? So that's a cool thing about the derivative, and that's one of the reasons that we value it. Okay, so that's one goal. And excuse me, one of the things you're going to have to learn how to do is actually use this idea of the derivative to tell us things about a function. That is, I give you a formula, and then you use the derivative to squeeze out information about the function and its graph from that formula. All right, so let me show you how this works. And I'm going to, again, I'm not telling you what the derivative is yet. I'm going to motivate it and give you ideas that will help you understand what the derivative is as we go forward. So let me back up further. So this was a statement about continuity. This was a statement about limits. Let's go back further and talk about functions. So a function is a rule that assigns to each input a unique output. So if we have an input axis, I'm not going to draw the vertical axis, but if we have an input axis and we've got an interval a to b of numbers that we're going to plug into a function, then what the function does is it takes a number and it like maps it up to something. Okay. Okay, so think of these arrows as pointing you to the place that the output value is of that input. So I want you to think of this blue interval here as if it's a piece of rubber, if it's like a piece of a rubber band, then the function is stretching the input interval. So this is the case of a continuous function because the rubber band isn't breaking at all. And that's going to be the most interesting case to us. But think of a function as like stretching an interval. Sometimes it doesn't have to stretch the interval, but a lot of times our functions do stretch an input interval, or it's valuable to think about a function doing that. So let me draw two pictures for you. So in both of these pictures, I want you to think of the x-axis. I'm not going to draw it, but I want you to think of the x-axis and the y-axis having the same scale. So like 1 centimeter on each axis is the same units of input and output. And I'm going to take an interval up here on the first example, and we're going to have an f of c here. It's going to be a nice continuous function. And my function is going to start here, and it's going to end here. So the graph looks like that. So what I want to point out to you, and what color should I use here? I'll use a light blue, is that if we look at the function values that we get, okay, so like here's f of a and here's f of b. Compare the lengths of these intervals, right? This interval here is much shorter than this interval there. So the function, you can think of the function as compressing the input interval from a to b into a much shorter interval from f of b to f of a. Okay, it's shortening an interval. Functions can do other things too. So here, if I've got the interval from a to b, it's a shorter interval. The graph could look like this. And here you can see the output interval is much longer than the input interval. So this is a case where f of x is stretching. Okay. So yeah, the function is assigning inputs to outputs in a unique way. And then we can think of a function as stretching or compressing the input interval. And so sometimes we can ask ourselves, it's useful to ask, what is the function doing? How can we tell if a function is stretching things out or compressing things? Okay. And I guess I'll try, without giving too much stuff away, the idea of stretching and compressing relates to the steepness of the graph. So you can see in the first case where we're compressing an interval, the function is not very steep, right? It's a nice gradual increase. Whereas the function that's stretching an interval, its graph is very steep. Okay? So in fact, the idea of a derivative is going to give us a way to talk about steepness in a very precise sort of way. Another thing I want to point out while we're doing this, both of these, well, let me draw it on a different set of axes. We can copy this to the next page. Okay, so we've got these graphs. I'm not interested in steepness right now, so let's get rid of this. One of the things I want to point out to you is both of these graphs are doing something that's important, and it's this. In the first graph, if I pick an x input here and then move to the right, so I let my inputs get bigger, well, if you look at those points on the graph, they climb the graph, and so their y values are going in that up direction. So the inputs down here, so how to say this? The inputs are going up and the outputs go up. Okay, that is, they have the same direction. The same is happening here in this other graph. But there are functions that don't do that. So if my graph was like the purple graph, then the opposite happens. As the x's get bigger and bigger, the y values decrease. They get smaller and smaller. Okay. So as the inputs go up, the outputs go down. And likewise here, if I had a purple graph like that, as the inputs go up, the outputs go down. Okay. So in these two cases, f of x changes the direction of the inputs. Okay. And then in the green case, f of x preserves the direction. Of the inputs. So these are two properties that would be great for us to be able to understand. And the derivative is going to let us know when a function preserves the direction or changes the direction. And so that's pretty cool. Any questions so far? So I'm just trying to summarize this idea that if a function, which is a rule that assigns to every input a unique output, a function can be thought of as stretching or compressing an input interval. And it can also be thought of as preserving the direction of inputs or changing the direction of inputs. And sometimes functions can do both, right? Sometimes a function can do this. So for part of the time, like from here to here, preserves inputs, and then for part of the time, it reverses inputs, and then for part of the time, it preserves the direction of inputs. Okay, so functions can change directions, and we'll want to understand when that happens too. Okay, so stretching, compressing, preserving, or changing directions. So now let me show you something. So here's a core concept behind the derivative, beneath the derivative. It's a foundational concept. If you can understand this, it's going to help guide your use of the derivative almost all semester. And it's this concept of local linearity. Oops. Okay. Nice functions are locally lines. Let's say it locally a line. Let me unpack this a little bit. A function that is nice, let's say, and smooth, or say smooth. Well, let's say is nice at x equals c is like a line near c comma f of c. Okay, so this is an idea that I want you to understand, and I'll show you a couple examples. The first example I'm going to show you is here on my iPad, and then I'm going to switch us over to Wolfram Alpha, and we can do a little bit of computational exploration. So the idea is this. So if I've got a nice function, and by nice, I kind of mean smooth. So there's a nice smooth function, like a graph of a polynomial. It's nice if it has the following property. So what I'm going to do is I'm going to zoom in to this rectangle. Okay, so in this rectangle, it looks like my graph passes through there, passes through there. It looks like that. And so you look at that graph and you think, oh yeah, that does kind of look like a line. That looks pretty straight, but it gets better. So let's do this. Let's zoom in even further. So in this rectangle, let's see, the graph comes in here and goes out there. And in that rectangle, it's really going to look, it looks even straighter. Okay, in this really zoomed in spot, which is right that way down in there, you don't see any of the curve that's happening from far away. And I could go even a step further and zoom in, and it would look straighter and straighter. Okay, so the question we have is, what is this line? Okay, this line that we're seeing is an important line to us, and so let's play a game with Wolfram Alpha to see if we can find the line. So I'm gonna share my browser. And if you don't like Wolfram Alpha, you can use Desmos or something. But let's plot y equals x squared on 0 to 5. So we can just see a plot here. And I think I'm gonna see if I can zoom in a little bit or make things a little bigger for you. Okay, so here's a graph of the parabola from 0 to 5. And so let's look here around x equals 1. So let's go from 0 to 5. Let's go from 0 to 2. Okay, so I'm claiming that right around here where the crosshairs are, if I zoom into there, the graph of my function is going to look like a line. Okay. So zooming in is easy when you're doing this by hand. Let's go from, instead of 0 to 2, let's go from 0.9 to 1.1. Right? So the x equals 1 is still right in the middle. That looks really linear, if you ask me, right? That definitely looks like a line. But I bet there's still a little bit of curve in there. So let's zoom in a little bit more. Let's go to 0.99 and to 1.01. All right, so that looks like a line. So the question I want to ask now is what is this line? So we know it goes to the point 1, 1. Let's find another point it goes through. And I don't think Wolfram does a really good job of telling us what this is, but maybe it's 1.005, 1.01. Okay, I'm going to write that down on my iPad. And I'll show that to you in a second. So line through 1, 1, and what did I say, 1.005, 1.01. All right, so now what I want you to do on scratch paper or whatever you have around you is calculate the slope of this line. Okay, it goes to the point 1, 1 and the point 1.005, 1.01. Okay, remember slope is rise over run. And then I'll give you a few seconds and I want you to put the number you get in the chat and we'll all hit enter at the same time. So when you get a number, and I just got a number here, I'll put mine in the chat. I want you to put a number in the chat too. And when you get a number that you can throw in the chat, throw a thumbs up onto the Zoom so I can see you got something. And I'll wait a little while until I see at least 5 or 6 people get a number. All right, Robert's got a number. Yeah, what's the slope of the line that passes through the point 1, 1 and the point 1.005, 1.01? Anybody else get the slope? Oh, Selena jumped the gun. But she got a number. All right, let's see people who've got a number. Go ahead and hit enter if you got something. Yeah, 2. So I get the slope 2. So I'm going to go up here in Wolfram. It says plot y equals x squared on this interval. And I'm going to say and y equals 2 times x minus 1 plus 1. Right, because I think using the point slope form for a line, this line would be y minus 1 equals 2 times x minus 1. So adding 1 to both sides, I get that. So we're going to plot these 2 lines on the same set of coordinates. So if we did it right, yeah, here you go. So there's 2 lines. One here is in red and the x squared is in blue. They line up. They line up perfectly. So good job, everybody. Now let's zoom back out a little bit. Let's go back out to 0.9 and 1.1. All right. So you can see they're starting to diverge at the edges here, right? The blue curve here, that's the parabola, and the red curve is that line we found. Let's back out to 0.5 to 1.5. All right. Pretty good. Now I'll go back out to 0 to 2. All right. So that's what that zoomed in microscopic line on the graph looks like when you blow it up. Okay. This is called a tangent line. I'm writing this down, is the tangent line to y equals x squared at the point x equals 1, right? This is a tangent line to the graph. And one of the first things you're going to need to learn how to do is how to look at a graph and find a tangent line. Okay. And you don't have to go through everything that we just went through to make a good guess for a tangent line. But what I want you to know is where that line's coming from. That line is actually the zoomed in approximation of the graph itself, right? And it's telling us really important things about the function. So yeah. So let me share with you my iPad before we do anything else. So this is what we just did. We had the function x squared at x equals 1. When we zoomed in to the graph at 1, 1, we got really, really close. All right. And what we saw was a line. The graph looked like a line. And it was a line through these 2 points. And so we calculated the rise over the run, right? So the difference in the y values divided by the differences in the x values, and we came up with 2. And so that told us the line we were looking at had this form, right? And just so you remember, this formula here I'm writing in blue now is the point slope formula for a line. With slope m that goes through x naught, y naught. Okay, so this is a very important formula for us. So you should have seen it when we were doing review. Okay, so we get this is the formula for that line. And then when we zoomed out, I told you that line is the tangent line. Okay. And in this case, it's the tangent line to the graph of y equals x squared at the input x equals 1. Let's do another. So somebody give me a function that's nice and smooth. Anybody have a favorite function we want to work with? Throw it in the chat if you have a function that you want to work with. Nobody? Log x? Oh man, you are a difficult person. Okay, so y equals log x. Is that a nice and smooth function? Yeah. We know the log function is continuous because it's the inverse of an exponential, and we know exponential functions are continuous. And we know from experience the graph is nice and smooth. So I'll say that it's a nice function. And for the log, let's say it's the natural log. So let me change this. The natural log. A nice input for the natural log is e, because we know that the natural log of e is 1. So this tells us that the natural log passes through the point e comma 1. So let's go look and see if we can find the tangent line for this function. So I'm going to go and share with you Wolfram Alpha again. And so here I'm going to say plot. We're going to get rid of this line. And we're going to plot log x. And I think Wolfram Alpha thinks that's the natural log. We'll see here. So it assumes the log is a natural log. Okay, that was a good guess. And yeah, so here's the graph of the logarithm function. E is about 2.7, so it's right around here. Or we could look here at 1. So we're looking right about there. Okay, that's the point we're interested in. Okay, and a function looks nice and smooth there. So let's say we want to plot it from E minus 0.25 to E plus 0.25. All right, so there's the graph of the logarithm. Looks nice and linear. I think you could believe there's a little bit of bend there, so we're going to zoom in some more. So we'll say E minus 0.1 to E plus 0.1. All right, that looks even straighter. Now you can be doing this at home. There's no reason that I have been the only person to do this. So we're going to zoom in just like we did on the x squared. We're going to zoom into that block. So let's find the slope of this line. So to do that, I'm going to have to find 2 points. So here I'm going to choose this x value. And so 2.715, and I'm going to estimate the output. Oh boy, what am I going to estimate that to be? It looks like it's 0.998. So it's just below the 0.999 mark. So I'm going to say that's 0.9989. And then I'm going to look over here at this input, 2.725. I'm going to go up here to the y value. And getting that crosshairs as close as I can. It's like 1.002. It looks like it's halfway between the 1.002 and 1.003. So I'm going to say this 1.0025. Okay, so I'm going to show you what I just switched back to my iPad so you can see what I'm doing. Because now I'm going to ask you to compute. You can do it. Come on, you can do it. There we go. So this is what I just wrote down. Now I want you to compute the slope. What's the slope of the line that passes between those 2 points? All right, so compute delta y over delta x, the change in the y's over the change in x. Use your favorite calculator. I think that's what I'm going to use. I'm going to go and put this in a calculator. And then when you have a number, throw a thumbs up into Zoom. And I use the reactions. As a reaction, you can put a thumbs up, or a clap. All right, I see some people got numbers. Let's give other people a second to catch up. All right, I'm going to type what I got into the chat too. All right, so I'm going to do a countdown, and then people can hit enter and show everybody else the number they got. 5, 4, 3, 2, 1, go. Yeah, right. We're getting about the same thing. One person got the digits reversed, but that's probably a typo. Yeah, okay, good. So what does that mean about the formula of the line? So take a second and guess I'm already sharing my iPad. Take a second and write down the formula for the line then that we have. So we have y minus oh yeah, wait a second. So yeah, no, I'm doing this wrong. Because we don't want just any line. We want the line that goes through this point. So we want to use the point slope formula with this point. Okay, so that's very important. So y minus 1 equals 0.36 times x minus e. So that's the formula that I get for the line that we're looking at. Hopefully you got the same thing. So I'm going to go back to Wolfram Alpha and I'm going to put that in here. So I'm plotting the logarithm function and the line y equals 0.36 times x minus e plus 1. All right, so we plot them both on that same tiny interval, and it looks pretty good. They don't look like they line up perfectly, but it looks pretty good. So let's zoom out a little bit. It still looks about the same. We'll zoom out more. Now it's going to look different. Yeah, there we go. Right. We can definitely see our line, the reddish line. And let's go to our original from 0 to 2 times e. All right. So there you go. There's the graph of the logarithm along with the tangent line at the point e comma 1. Right. And this tangent line, we came up with 0.36 times x minus e plus 1. That looks pretty good. It's not exactly right because our calculation of the slope was an estimate, but this looks pretty damn good. Good job. Okay, so what we're going to try to do now is after we take a break is we're going to talk about how do we find a formula for a tangent line without having to go through all these hoops, right? Because this really was only finding an approximation. How can we find the exact formula for a tangent line if it exists? Okay, but let's take a 5-minute break first. And I'm going to start the timer in a moment. And then 5 minutes, we'll all get back and keep talking about math. All right, just started it. All right, see you in 5. All right. Time's up. Let's get back to math. Music paused. You guys can still see my iPad, I trust. Oh, no, you're seeing Wolfram Alpha. All right, let's go back to my iPad, which is asleep. Wake it up. All right. All right, so any questions on anything we've done so far? No questions? Everything seem reasonable, seem good? So this little exercise of picking a function and picking a point and then trying to find or estimate the tangent line is a great estimate. Go do it playing with Desmos, do it playing with Wolfram Alpha, and just see if you're able to make good estimates of what the tangent line is based on what we've been doing in class so far. All right, so my Apple Pencil here is low. I need to reshare this in a different way. I can do it this a different way. So what I want to do is I want to approach this differently, and I want to show you how we can actually calculate the tangent line, much in the way that we calculate limits. And it'll take me a little while to work up to that. So let me get a new page here. So next, I forget this. I also want to show you how to sketch a tangent line. What we just did is a great way to estimate a formula for a tangent line, but that's if you're just drawing pictures. If you just want to see a gut level or just a real intuitive tangent line, there's other ways you can do it. So I want to talk about that, how to sketch the tangent line, rates of change, and then start getting to some formulas. Okay, so how to sketch a tangent line. So let me show you how to sketch a tangent line. And I wonder, maybe I should do a screencast on this. You can't see my pen. So here's a graph of a function. Say somebody wants you to sketch a tangent line here at x equals c. Well, then you go up to the point on the graph, c comma f of c, and that's where you want to draw the tangent line. So I'm going to draw a couple things that aren't tangent lines. That is not a tangent line. This is not a tangent line, okay? Because they don't have that sort of feeling that the tangent lines we just saw had. Here is a tangent line. So I'm going to put my pencil at the point, and I draw it half at a time. So there's part of it, and then I go back to the point, and then I draw the other part. That's a tangent line. Okay, that's what a tangent line looks like. So some common features of a tangent line: it touches only at one point. Okay, I'm going to put an asterisk there. It stays on one side of the graph. I'm also going to put another asterisk there. Maybe we'll put a double asterisk there. Yeah, those are the two common features of a tangent line. There are some tangent lines that don't have both of those properties or fail to have one of them, and I'll give you examples of those a little bit. So I'm going to say asterisk and double asterisk. Not always true, but most of the time they are true. Okay. A lot of people like to describe a tangent line as the way it touches the graph is it kisses the graph, right? And that's the difference between the green tangent line here and the way it's kind of kissing the graph at one point versus these two, which are cutting through the graph, just, really brutally cutting through the graph itself, punching through it. The green line is not punching through. It's just kind of, it's coming up alongside and it just barely touches it at one point and then keeps going. Okay. So that's what people mean when they say the tangent line kisses the graph at a point. It doesn't punch through. It just, it sidles up, touches it, and then goes away. So a couple examples I thought to show you: y equals x squared. Nice parabola. If I pick a point here, that's a tangent line. Or pick a point here, there's a tangent line. Or if I pick the vertex, the tangent line's horizontal. Y equals cosine of x. Now this is a graph that's hard to sketch. But I'm going to say it kind of looks like this. And just pick a point. tangent line there. You're down at the very bottom. The tangent is going to be horizontal. Tangent line over here. So these are all places where the tangent line have these features that I bullet pointed over there. Another important case of a tangent line is when you've got a straight line. Pick a point on the line, and the tangent line coincides with the line. And so that's something that's important to remember, is that the tangent line to a line is the line itself. All right, so let me show you a couple of the odd cases, a couple of cases where the graph isn't staying on one side of the point, or it isn't just touching the graph at one point. Okay. I should say also that these two properties, asterisk and double asterisk, are local properties. All right, and I'll explain what that means in a second. Doesn't stay on one side. So here's an example of a function, y equals x cubed, that has this property that the tangent line seems to disobey, or doesn't have those two properties that I pointed out. And this is the tangent line at 0. A tangent line at x equals 0, the tangent line is a horizontal line, and it cuts through the graph. Okay. But it does have this kiss property, but it cuts through the graph. It doesn't stay on one side, and that's okay. Let's look at this in Wolfram alpha, so you can be convinced that the tangent line is actually the tangent line. So I'm going to plot y equals x cubed and y equals 0 on the interval from -2 to 2. All right, and you'll see, oh yeah, that does. Okay, we'll zoom in here. You can faintly see the red tinge of the line y equals 0 here. But you can see how the y equals x cubed comes in to the x at 0 almost horizontally, and then comes out almost horizontally. And the tangent line here, it's tangent to the graph. It's like it wants to kiss at one point, but it has to pass through. This is just a reflection of the fact that the cubing function is really flat around x equals 0. Okay, and so the tangent line has that property. So going back to my iPad. Okay, so you can see my graph of x cubed wasn't super flat, wasn't as flat as it should be around x equals 0. Another function that has this property is cosine. At x equals pi. I think that's what I want. No, not pi. Pi over 2. Is that right? Again, I didn't draw the graph really great, but the tangent line looks like that there. So let's go look at Wolfram alpha and see what it tells us about the cosine and its tangent line at that point. So let's say cosine of x, and I'm going to say y equals, what is the graph here? Something times x minus pi over 2. That's going to be plus 0, and the m is minus 1. Let's see if I got that right. And we're going to go from 0 to pi. Oh, typo. Cosine of x in that line. Okay, so there you go. Blue is the cosine curve. The red curve is what I claimed the tangent line was. And you can see here, yep, that looks like a tangent line. And yeah, you can see it's crossing the graph of the cosine. Okay, at this point. Okay, that's because the cosine really kind of straightens out when it crosses the x-axis. So tangent lines don't have to just stay on one side of a line. It could cross the line. And we'll talk about when that happens. What properties do a function have that makes their tangent lines cross? But something I want to point out to you here, let's do this. I'm going to move back a little bit to say pi over 4. And I'm going to that's this. This is the tangent line at pi over 4. Let's see if that works out. Yeah, so here's another tangent line. So here's a tangent line at pi over 4 comma root 2 over 2. Okay? So it looks good here. But notice what's happening way down here. I'm going to plot this on a slightly larger. So let's go to 3 times pi over 2. Notice what's happening further down the x-axis is that the tangent line does intersect the cosine graph. Okay. Sometimes that's going to happen, and we're okay with that. Don't worry about that. It's right around here where you're talking about the point of tangency that you only want it to intersect once. Okay. And it's a local property. So single intersection around here. Far away, it might intersect the graph. That's fine. But nearby, we only want it to intersect once. Okay. So back to the iPad. Which is asleep. Here, I'll draw this on the cosine graph too. So there's the picture that we just saw in Wolfram Alpha. Of 2 points of intersection, but only one of them is local. Okay, so that's my summary of sketching tangent lines. There's one more thing I want to say about it. But the idea is when a function has a graph that has a tangent line, that tangent line generally kisses the graph and only intersects the graph locally once. Those are the 2 principles. So when you're playing, when you're just when you're learning how to do this, right? You plot a graph and you want to estimate a tangent line or find a tangent line. It's easy just to draw the line. The next thing you want to do is you want to estimate the equation of the line. So generally we use the point slope formula because you know what point you're intersecting your tangent line at. Okay, so you have that. And then at that point, you want to estimate the slope from your sketch. And I just want to remind you how easy that is. Okay, it should be easy for you. So here I'm going to put some tick marks on my axes here. I'm going to try to make them uniform. And I'm going to put a graph in here. So let's say here's a graph of a function. And I'm going to say I'm here at the point 4 comma, looks like 2.5. And I want to estimate the formula for the tangent line. And it's a pure estimation. And nobody's going to expect us to get it perfectly correct. Okay, so I'm going to sketch in the tangent line. All right. So I know what the values of x naught and y naught are going to be in the formula. Now I just need to estimate what the slope is going to be. So let's just extend this and extend that up. So slope is rise over run. So really what you need to do is you need to draw in a right triangle and figure out what the lengths of the sides of the right triangle are. And you can do that wherever you want. And I strongly suggest that you make the biggest right triangle you possibly can. So I'm going to do this with a gray. So I'm going to come down here to x equals 1, and I get that point on my line. I'm going to go up here to x equals 7, and I get that point on the line. And then looks like my rightmost point has a height there of about just slightly less than 4, and my rightmost point has a height that's slightly less than 1. And I'm going to say that this difference here looks to be 3. And by my choice of the endpoints, I know that this distance is 6, because I got to choose where those dots were, right? I chose that point and I chose that point. Okay, so you always can make one choice and one computation easy, right? The 6 was easy. We really lucked out here on the 3, because this gap right here, I'm just saying, is about the same as that gap. So then I conclude by saying delta y over delta x. In this case, it looks like if I go up 3, no, if I go up 6 in my x value, my y value goes up 3. So my slope here is 1/2. So it looks like my tangent line has the formula y minus 2.5 equals 1/2 x minus 4. Okay. So that's how you estimate the formula for a tangent line. And what I'll tell you right now is, generally, as we do this work, it's this estimate, the estimate of the slope, that's the most important thing for us. So it turns out that the derivative of a function is really tightly related to the slope. So that's the work that you do when you're estimating a tangent line. That's the important work. Okay, any questions about this so far? I'm not seeing any. Also can't see the chat. Okay, there we go. Now I see the chat. Okay, so I've told you that we're interested in tangent lines. I've showed you where they come from, right? From zooming into a graph of a function. And I've told you what they look like, right, when you zoom out. And that's pretty cool. And then I showed you how to sketch them. If I give you a graph, how do you sketch a tangent line? And I don't want you to underestimate how important that skill is. And so you should really practice this, right? Practice it while you're watching TV. Practice it. You can't practice while you're playing video games or something, but just practice it all the time. Do a lot of practice. Practice sketching tangent lines, and then practice estimating their slope. That's an important skill. So now I'm going to show you how we compute it. And you might think computing is the most important, but I think estimating is the most important. If you can't estimate, then you're never going to remember what a derivative means, and the rest of the course is going to be really hard. So being able to estimate is super important to me. Okay, calculating a tangent line. So how do I start? So when we have a function and we've got a tangent line at a point, the slope of that tangent line has a meaning. M is the instantaneous rate of change of f of x at x equals c. So this is a concept that this is a derivative, instantaneous rate of change of a function. And it's going to give us all kinds of cool information about functions. But it's the slope. The slope is the instantaneous rate of change. So let's talk for a second about rate. Can somebody give me an example of something in our life that's a rate? APR, yeah. So APR, what is that? Annual percentage rate. Right, and that's like percent per year, right? I think APR. Velocity, miles per hour, right? Velocity, miles per hour, kilometers per hour, right? So these are very common rates, and it's this velocity. Velocity is going to become a rate that we'll talk a lot about. But what I want to point out to you is that a velocity is a quotient. The unit on a velocity is something per something else. Okay. And when we're talking about slope, slope is a delta y over a delta x. Okay. So the unit on a slope is a rate. So when you've got a function, if we talk about a tangent line, the slope of that tangent line is a rate because there's going to be an input unit. There's going to be an output unit. Right? And the unit on the slope is going to be inputs per output. So an important example of this is a position function. So say I've got a position. So t, the input is the amount of time that elapsed, say in seconds. And s is distance, or let's say position. Of an object, say measured in feet from something. Then delta S over delta T is measured in feet per second. And that's a unit of velocity. So if you're graphing a position function and you're looking at a tangent line to a position function, the slope is measured in is a representation of some sort of velocity. Okay. And that's the sense in which these slopes are an instantaneous rate of change, right? That unit per unit. All right, so instantaneous, what does instantaneous mean? Well, it's something that happens at an instant, right? It's something that happens immediately. So the change in time to make an instantaneous measurement, the change in time here is 0. Okay, that's what it means to be an instant. There's no change in time. So that's going to make measuring instantaneous velocity a challenge, but let me get to that. I think I'm getting ahead of myself a little bit. So how to calculate slope of a tangent. So let's say I want the slope of this tangent line. I know the function goes through c comma f of c. So I know the tangent line goes to that point. If this is all the information you have about the function, right? You've got the function goes through c comma f of c. You don't have enough information to calculate the slope of a tangent line. Okay. If all you know is c comma f of c, you can't calculate the slope of the tangent line. Okay, but Suppose delta x is small, and you know c plus delta x, comma, f of c plus delta x. That is to say, up in the picture, I'll draw it in blue. You have this other ordered pair. Well, now with these 2 points, you can connect these 2 points with a line. Okay. 2 points determine a line. Okay, so you can calculate the slope of this line. Delta y over delta x is f of c plus delta x minus f of c all over c plus delta x minus c, which simplifies to f of c plus delta x minus f of c all over delta x. So here's a key idea. If delta x is small, delta y over delta x is approximately equal to m, where m is the slope of that tangent line. Okay. This green line is called a secant line through c comma f of c and f of c plus delta x comma f of c plus delta x. Sometimes it's called the secant line on c comma c plus delta x. Okay. And this idea that the slope of the secant line is going to be close to the slope of the tangent line if this horizontal distance between c and c plus delta x is small, that's really important. Okay. Let me copy this and say a couple more things. One other thing that I wanted to say, is delta y over delta x. So this thing here is called the average rate of change of f of x on c to c plus delta x. Contrast that with what we were talking about on the previous page. I'll just swipe over, 2 over. Instantaneous rate of change. The slope of the tangent line is the instantaneous rate of change. The slope of the secant line here is the average rate of change. And the idea is that the slope of the secant line is taking into account all these instantaneous rates of change on this whole interval and presenting their average. So the slope of the secant line is like the average of all the instantaneous rates of change here. But then as you take this point and you move it closer and closer to the starting point, the slope of the secant line gets closer and closer to the slope of this tangent line. So that is to say, the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x is the slope of the tangent line at x equals c. So I could write that in here, m equals that limit. So this is how we calculate slopes of tangent lines through limiting processes. Some representations of functions don't let us take limits, like numerical representations, and we can only do average rates of change. But there's this idea that the average rate of change approximates the instantaneous rate of change. So we can still talk about approximating derivatives with some representations. But if we have a symbolic representation of a function, we can calculate derivatives using limits. And that's what our focus will be on in this course, is symbolic representations of functions using this. Okay. So let's do an example. So we've got a few more minutes, right? Yeah, we got. So find the equation of the line tangent to y equals x squared at x equals 1. So let's find that equation. Okay, so the picture, of course, is going to look like this. The tangent line is going to be like that. And what we need to know is that x is 1, that's the input is 1, and so the output is also going to be 1. Okay, so x naught, y naught is the point 1, comma 1. So the formula we're looking to finish out is y minus 1 equals m times x minus 1. So we need to calculate that m. And we're going to use this formula to do that. So we'll start here and I'll have to go on to the next page. M equals the limit is delta x goes to 0 of f of 1 plus delta x minus f of 1 all over delta x. Okay, so that's the limit we want to calculate. I'm going to move that to the next page here. All right, so I'll keep copying the limit statement. So my function is the squaring function, so I'm squaring 1 plus delta x. F of 1 is 1. So squaring that expression there, I get 1 plus 2 delta x plus delta x squared minus 1. All right, now you might say, okay, well, let's evaluate this limit and let's do the naive evaluation of the limit. And if you do naive evaluation, you're going to get 0 over 0. Right? So on the one hand, you go, oh! On the other hand, you go, something interesting is happening. And you just have to do some algebra. So this 1 cancels with that 1. And then you look at the numerator and you see each of those terms has a delta x in it. So you can factor out a delta x from the top. And your numerator factors to this. And then you see, that delta x in the denominator that was giving you division by 0 cancels with the delta x in the numerator, leaving you with this really nice expression, 2 plus delta x. And that's a polynomial in delta x, if you care to look at it that way. But here you can use naive evaluation, and you get 2 plus 0, which is 2. So that's your m. And if you go back to the point slope form that we had, you'll see you just calculated what that m is. And so the formula you have is y minus 1 equals 2 times x minus 1. So now I strongly encourage you to check your work. So you'll open up Desmos or Wolfram Alpha. So let me go back to one of them. Oh, it's gone to sleep, so pardon me for a second while I wake it back up. Okay, it's woken back up. Share. So I'm going to tell Wolfram Alpha to plot y equals x squared and y equals 2 times x minus 1 plus 1 on the interval 0 to 2. And hopefully the picture will look right. Yeah, that looks good to me. Right, I've got the parabola here, the squaring function, and I've got my line, and my line definitely looks like a tangent line. It looks like it's kissing the graph, the parabola at a point right here at 1, 1. That looks great. So this gives me evidence that my answer is correct. My calculation was correct. Okay. All right, so that's how you're going to calculate tangent lines or slopes to tangent lines and figure out their exact formula. Okay, using these limit processes. So one thing that I want to point out to you, so we just calculated the instantaneous, I should share with you my iPad now that I'm moving back to it. Share, share, share. You can do it. There we go. We just calculated that the instantaneous rate of change of this function at x equals 1 is 2. Let's look at the average rate of change. On a couple intervals. So let's look at it on the interval from 1 to 2. Okay, so let me sketch the graph over here. So we're talking about y equals x squared on this interval from 1 to 2. So if we do that, we get delta y over delta x equals 2 squared minus 1 squared over 2 minus 1. Because I'm calculating the slope of this secant line. So that's 4 minus 1 over 1, which is 3. So that secant line, you can see from my sketch there, the secant line is steeper, has a steeper slope than my tangent line. Okay, that average rate of change over 1 to 2 is bigger. But if I calculate the average rate of change from 1 to 1.1, I'm going to get a smaller number. So 1.1 squared, I think, is about, is it 1.21? And so I get about 2.1 for that average rate of change. And you can tell that on this interval, that secant line, it's going to have a slope that's a lot closer to the slope of my tangent line. Okay, so this is what's happening with average rates of change on intervals that are close to or contain a point at which you've got a tangent line. Looking at the other side, interval from 0 to 1. So this is as if like delta x equals -1. So you can have deltas that are negative. What's the slope of the secant line, or the slope of or what's the average rate of change on that interval? Well, it's 0 squared minus 1 squared over 0 minus 1. So this is showing us that the slope of the secant line here is 1, which has a slope that's less than the slope of my tangent line. But then if I make my interval smaller with my x equals 1 as an endpoint, notice what I'm getting here. So I think I'm getting 1 minus 0.81 over 0.1. And this looks like it's going to be about 1.9. And so those numbers are getting closer and closer to 2 as my interval gets shorter and shorter. This is what's happening with secant lines, slopes of secant lines. And a lot of textbooks, including our own, will ask you to use secant lines to approximate or estimate the slope of a tangent line. Okay. What they're asking you to do is basically here, this is a slope of a secant line. Make that delta x smaller and smaller, and you'll get better and better approximations of your instantaneous rate of change, your slope of your tangent line. Okay. Any questions about this? So to summarize, oh yeah, and I'll bring it back around to the beginning. That would be a good idea. What did we talk about today? We talked about how to sketch a tangent line. We talked about a tangent line is the local linear, how to say that? The local linear representation of a function. And this is where we zoomed in. We talked about how to estimate slope. We talked about slope of a tangent line as instantaneous velocity or instantaneous rate of change. We talked about a slope of a secant as the average rate of change. And then we talked about how to calculate exactly the slope of a tangent. Okay, so these are the main points today that you need to understand and be able to work with. So let me bring it back to what I was talking about at the beginning of class, and this idea of functions stretching and compressing intervals. So if we have a function here that looks like it's stretching an interval, how does that relate to what we were just talking about today? Well, stretch seems to go with a steep tangent. And steep being m is big. Okay. So if a function's stretching an interval of inputs, if it's got a steep tangent line, if it's got a big tangent line. Conversely, if a function isn't stretching very much, right? If it's compressing, then the tangent line has a small slope. Okay. So maybe I didn't use the word not stretching, I said compressing. Okay. And then I also had talked about this idea of directionality. And what we've just learned is that preserving the directionality corresponds with the slope being positive and reversing corresponds with slope being negative. Okay. So suddenly these tangent lines are giving us ways to talk about geometry of functions that tell us about their behavior. So letting us go from that really simple understanding that we have just from the limit alone, now using this idea of the limit of slopes of secant lines or the limits of these average rates of change to get to the slope of this tangent line, it gives us a lot more information about what a function is doing. And this is the basis of the derivative, and this is what we'll be studying for the next 3 or 4 weeks. And if you can understand all the stuff we're talking about now, heading into the talk about the derivative, it's really going to help. But if you keep circling back as we talk about derivatives, if you keep circling back to what we talked about today to reinforce how these ideas are related, that'll strengthen and deepen your understanding of derivatives too. So don't feel like you have to understand this all right now. But yeah, these are all important foundational concepts for the derivative. And I'll end it there just a couple minutes early. Remember, class on Friday, we're going to start late. I'll send out a Canvas announcement. We have provost candidates on campus this week again. So this will be the last day that I cut back on class. So there's screencasts you can watch to make up for a little bit of that. But yeah. All right, that's it. See you all on Wednesday. Bye-bye. See you then.
Thank you.
Yeah.